oriented by gamma in this way. Now we want to construct an opposite orientation by using a mapping. So what is the proper mapping we choose? So we can think about that, well, this one can be, think about minus beta. Okay. And this one can we think about this gamma, minus alpha. Okay. Because alpha is less than beta, so minus beta is less than minus alpha. Alright, so we have another interval from minus beta to minus alpha. Okay, and so if we define, so we can go this way. So if we define gamma tilde to be in this way, that alpha t, gamma t is defined to be minus t, okay, the laboratory. Okay, so now when t is equal to minus beta, then minus t becomes beta, so this one is start from here, right? Minus beta. When it's moving up to minus alpha, then the curve will move in this way. So the direction will be this way, right? So this maybe, by this definition, I just define a gamma tilde to be gamma of minus t. Okay? And so that the parameter interval becomes from minus beta to minus alpha. Okay? So when it moves up this way, it will move. Okay? Just like if we move from alpha to beta, it will move from this endpoint to the other point. So we call, so we now know one way of, so we know that we call gamma to be the opposite of gamma. Okay. And we usually denote gamma tilde as minus gamma. Okay, so we use minus gamma to denote this function. So actually, so minus gamma t, what is that? Actually, it's gamma minus t. Right? Just definition. Okay, the thing is that if so we know that gamma star is equal to gamma tilde star, and this is just minus gamma star. Okay. So now if f is continuous on gamma star, then if we evaluate this line equal, alright? So if we evaluate this line equal, the opposite or the reverse of gamma, okay? So when we evaluate that, by our definition, this is from minus beta to minus alpha, okay? And the f, okay? Gamma tilde b, gamma from b dt. This is by definition. But note that the gamma tilde from t is what? Is gamma from minus t times minus 1. Okay? By chain rule. Okay? So we have minus alpha, minus beta. And by definition, this is gamma minus t. Okay? And this one is gamma from minus t times minus 1 times dt. So we have And then and this is I observe my one here, and I change the value of x, define x to be minus t. So this comes to beta and alpha because minus t, and the f of gamma x, and here is gamma prime s and here, and which is equal to minus from alpha to beta f gamma x and prime x. So this is minus gamma fg. So prove that if we evaluate the line integral along the opposite of gamma, the result is equal to minus times the line integral over gamma itself. So is that okay? So you see, even though gamma star and its opposite, minus gamma star, they have the same image, right? Because of the different orientation. Because of different orientation, you have the same f, right? The same f defined on the same image. But because of the different orientation, the line integral has different sign. Okay? So the orientation doesn't matter because it will affect the sign of the line integral. Any questions? Alright, so let's do some example. So examples. First one, suppose gamma is the positively oriented unit circle. Right? So the unit circle means that the center is 0. Right? The center is 0. i.e., so the positive oriented circle, okay, with center 0 and the radius point. Okay, so that is this one, and positive oriented. Okay, so this is our positively oriented unit circle. Then suppose so we usually because it's closed, so if a path is closed, we usually line integral, we put a circle here. It's a convention to just indicate that this path is a closed path. Okay. Right? So we evaluate this line integral. So f of z is 1 over z, and it's well defined. Why? Because the image, the unit circle, does not pass through the origin, right? So this is fine. Okay, and so we know what is the gamma. All right, so gamma actually is e I 2 pi t. Okay, and t is in 0 to 1. This is our parameterization, or maybe. All right, so by definition, it's from 0 to 1, and the z is e I 2 pi t. And what is gamma prime t? Well, gamma prime t is I 2 pi e I 2 pi t. Okay? Then 2 pi t here. Alright? So this is I 2 pi times e I 2 pi t and pt. And then you cancel. Okay? So the integral, so you got I to pi. Okay? So this is our result. Okay? So very interesting. The function 1 over z is a function defined in the complex bracket except the origin, right? You have this function. So the f of z is 1 over z. Okay? You have this function. And you integrate this function along the positive oriented unit circle. You go around it. Okay? Just one. Just once. Only one. And you find the value is a complex number is I times 2 pi. Second example. So this time gamma is a positive oriented circle with center A and radius rho. So we have rho here, EI 2 pi t. T is 0 to 1. Okay? So A is a complex number, okay? A is a complex number. So A is C, rho equal to 0, right? So this is the partially oriented, positively oriented circle with center A and radius rho. All right, and our function is z minus a raised to the mth power. Okay, that's mth power, and the m can be any. Right. Now, if m is minus integer, it is a negative integer. Now, z cannot be equal to a. Otherwise, it's not undefined. It's undefined, right? But if m is a positive integer, no problem, right? Okay. But in general here, right, m be negative or positive or 0. But here we are very fortunate because the curve that comes to a. Right? Because this is a circle with center A, so we don't worry about that, right? So f of z always continuous on gamma side. Okay, so now let's see the derivative actually is equal to I 2 pi rho E I 2 pi t. Right? So we have a derivative here, and now we can evaluate that. Okay, so our evaluation, so the parameter t is from 0 to 1. Okay, and here is rho to the m. Okay, v minus a, right? So a, this is minus a, we cancel a, so you have this one, so to the m, and the e, I 2 pi mt. Okay, and times here, times the I 2 pi times rho E I 2 pi t and dt. So that is good. That we have. And now we move 2 pi I, the constant, and the rho to the m plus 1's power. Okay, and from 0 to 1, E I 2 pi m plus 1 t and dt. Now, we have two cases. If m is minus 1, if m is equal to minus 1, this is 0, right? And this is 0, then the integral is 1. So the integral is 1. So you got 2 pi I when m is equal to minus 1. Okay? Because when m is minus 1, this is rho to 0's power, so it's equal to 1. And the interesting thing is that if m is not equal to minus 1, then it becomes 0. 1. But now you have cosine in the real part, sine in the imaginary part, right? and you integrate how many cycles? How many cycles? You integrate over m plus 1 cycles. Okay, whole cycles. So the real part is 0 and the imaginary part is 0, of course. Right? You know that? Cosine 2 pi mt is 0 for all m not equal to 0, right? Always. And the sine is the same. And always 0. You know that? So the integral, very interesting, that except m equal to minus 1, the integral is 0. But when m equal to minus 1, then this integral is equal to 2 pi r. Okay? So 2 pi r just like this one. Okay, you have this is z minus 1, right? So this is a special case of that. Can you see that? Right? A special case of that. When a is 0 and m is equal to minus 1. Furthermore, suppose that we have a function defined in the, so this is the real part of z, but it's x. Okay? Suppose we have a function. This function just take the real part out from z. Okay? So it's a very strange function, just take the real part out. So you can see it's not smooth, it's very strange. Okay? Now, we consider two paths. Okay, so we consider two paths like here. There are two different paths. It's from 0. So this is 0 to what? To this point. So this point is 1 plus 2i. Okay. And we have things like here. So actually, okay. All right, here. All right, this gamma 1 from 0, 1 we go to there, and gamma 1 t is equal to t plus 2i t. Okay, so it's this describes the line segment. This is line segment. So gamma 1 is describe the line segment. Okay. And gamma 2 consists of two parts. Gamma 2 consists of two parts. First of all, going here and then going there. Okay. So all right. So gamma 2 t is equal to t when t is in 0 to 1. Okay, so go here, and then gamma 2t is equal to 1 plus I t minus 1 for t from 1 to 3. Okay, so this is the, so we have 0 to 3 from here. This is gamma 2. So basically, we have two paths, right? This path just go directly from from here, in the line segment. But for the second path, we go horizontal to this point and then go vertical to here. Okay, so we have just two stages for gamma 2. So gamma 2 from here to there. Okay, so now we evaluate FZ, okay, EZ. Okay, the FZ is just the real part. Now, for gamma 1, from 0 to the 1 plus 2i, the real parts of t plus 2it. Okay, and we know gamma 1 from t. Gamma 1 from t is 1 plus 2i. Okay, gamma 1 from t is 1 plus 2i. So times 1 plus 2i and et. Just do the substitution. And this real part is just t, right? 1 plus 2i and dt. Alright? And after you evaluate, this is quite simple. 1/2 plus I. Okay? So gamma 1 is this one. Gamma 2. Right? So we just do it in the real part of t. Okay, and here in this branch, the gamma 2 prime is equal to 1. But in here, the gamma 2 prime is equal to I. Okay? So for the parameter from 0 to 1, it's the real power of t times 1 times dt. Plus from 1 to 3. 1 to 3, right? So real power of 1 plus I, t minus 1, times I, dt. Okay? Alright, so for here, we have 0 to 1 t dt. Plus from 1 to 3, this is I times dt. Okay? So the result is 1/2 plus 2i. And you see that these two integrals are different. So we know that gamma 1 fz dz is not equal to gamma 2 fz dz. So they are different. So they are different. Yep. So it's possible to know that even though we have two different paths with the same starting point, same ending point, but they are different paths, right? Then we end up with different line integral. Okay, with the same integral. Okay, so this is possible. Right? And later on, we will prove if f of z is smooth, for example, it's analytical. Alright, then we will see that in some geometry of the defined image, if f of z is defined in some domain, defined in some open and connected, and with some geometry properties, will prove that if you have different paths, but if their starting point and end point are the same, then you will have the same line integral. Okay, so we will provide some general properties about fz as well as the geometry of the defining domain, defined set of fz. So fz itself plus the domain of the set such that the f of z can be defined. Right? Will determine whether this is become to quality. Even you have different paths, but they are starting from the same point, ending with the same point. So we will prove that theorem. That will be Cauchy's theorems later. All right. So I think we have. All right. There's one inequality which is quite useful. Now, since the parameter interval alpha beta of a path gamma, okay, is a complex set. The complex means that a closed and bounded, okay, a closed bounded set in R. So any closed and bounded set in R is called a complex set. Actually, the concept can be extended to Rn. So any closed and bounded subset in Rn is called a complex set. Right? A complex set is continuous image gamma star. Because we know a class is continuous function, so this is called a continuous image. It's also a complex set. I.e., a closed, right, and bounded set now in C. Right? So gamma star for any path, the image of the path, okay, must be a complex set. So it should be a closed and a bounded set in C. Now, again, if a complex function f of z is continuous on the complex set, gamma star, then the image f gamma star is also complex. Okay, in C. In the point. So continuous image of complex set must be complex set. It's a topological property. So I don't want to prove that, but this is a fact, a mathematical fact. Right. So any complex set in the complex plane must be bounded and closed. Okay. So that because it is bounded, so that there exists m greater than 0 such that f of z, the magnitude, is less than or equal to up to m for all z in the image of K. Okay. Because that because this is a complex set, so we can always find an m here. When we find the m here, we now evaluate the line integral and to approximate. So then we have gamma fz. So the line integral, okay, we know this is alpha beta f gamma t gamma prime t and t. All right, and we know that the image of f on gamma star is bounded, so we know that this is M, and the gamma from T, and dt. And what is that? Actually, this is the arc length of the path. So this is equal to M times L. Where? Is the arc length of the path. Okay, so we know that for the any line integral, this is the arc length. So we can form the any line integral, okay, by a sufficient big number m times the length, the arc length of the path. Okay? So please understand that. So you have a lesson 1, complex set in Rn are those closed and bounded subset. In the first part, so you have to know very useful fact. Right? So in Rn, when we mention complex set in R means that just closed and bounded set. The second thing is that the continuous image of complex set are compact. Okay, so just have these two notions. Okay, so so if you have a complex set in plane like this one, and you have a hole here, so this is a complex set. Complex is bounded and closed, so it includes the boundaries. Okay, so this is a complex set, and you have a mapping F here. F is continuous. All right, so F is continuous. You know it's continuous. Then so this is say E. Usually we say A. All right. Then F8. Then F8 is also compact. So it must be bounded and closed. So if A is so when A is compact, as I know, compact means closed and bounded. Okay, and F of A must be compact because it's an image of a continuous function. So continuous image, okay, of complex sets are compact. So this is general principle you can use. So you know you can have fun. And in Haeckel's, the extreme value theorem is just a special case of these two concepts. Okay? Extreme value theorem tells you what? If you have a continuous function on an interval, okay, and F is continuous, right? What do you have? You will have maximum and minimum value. Why? Because this is a complex set. It's bounded and closed. So the image should be bounded. Once it has bounded, you know it will have, and it's closed, okay? So it's proper this way. Okay, so the image is here. Okay, and so it's bounded, so it has this upper bound and a greatest lower bound. But because it's closed, so the greatest upper bound, the greatest lower bound will be in it because it's in the boundary. And if any closed set include the boundary. So you get the minimum value. And this upper bound must be on the boundary. And because it's closed, so it will include the boundary point. And so that so the image has the maximum value. This is what you have, why you have the extreme value theorem in calculus. That's simple, right? It's the application of these two principles. Okay? So this is the extreme value theorem, basically. So you will have, so f is continuous, and so if you have a continuous function from a closed finite interval, go to here, then the range, then its value has the maximum value as well as has a minimum value. And what I am saying here, just apply the same principle. Okay, I apply the same principle here. Because this is true to Rn, okay, n dimensional. The ever n is that this is always true. Okay? Alright. So we are going to a more interesting subject. The next topic is the Cauchy's integral theorem. Right? And it's actually theorems. There are quite a few theorems with the same name, Cauchy's integral theorem. So I will give several versions. And at the end of this chapter 14, I will give you the global Cauchy's theorem. Global, no restriction. Okay. Of course, I can't. I think I don't need to supply. Well, depends. Maybe I just give the result without proof. I will refer you to a good textbook to see the proof. Alright, so I want you to just follow my logic. Because to give the proof is pretty time consuming, it's impossible. So I just give you the result and explain the idea. The first one is quite simple, right? So theorem A. Alright, f an analytic function, right? On an open set. Right, in the complex bracket. So omega is an open set, just any open set. Gamma is a closed path. Okay? Closed path means the starting point is the end point. Okay? So it's closed. In what? In the open set. So means that actually the gamma star included in omega. Okay, so that is the meaning. So when we say the closed path is in an open set, means that the image gamma star is contained in this open set. Okay, and we also, if the derivative is continuous, right? This is the assumption. So f is already analytical, means that f has derivative at every point of the open set. Okay? But we also require the derivative is continuous. Okay? We also require. And where in continuous? from omega. Okay? Then the line integral along the cross path with integral, which is the derivative of f of z. This line integral should be equal to 0. Right? It's very simple. It's very simple. Right? So basically, if f is continuous differentiable, right? Just say f is continuous differentiable on an open set. Right? So f just continuous differentiable, and gamma is just any cross path in this open interval. And when you evaluate this line integral over the derivative of f, the result is always 0. Okay? And the proof is immediate. So by the chain rule, right? The composition, okay? The composition. So the composition of the derivative is f prime gamma t gamma prime t. Okay, so that is it. For those in such that gamma prime t exists. Okay? Because gamma is path, right? Path is piecewise continuous only, right? So maybe at some t, the derivative of gamma does not exist. But if it does exist, then we should have a chain rule, because f is differentiable. Okay? F is differentiable. All right. So first of all, this is from chain rule. We have this knowledge. Now, when we evaluate this line integral, okay? When we evaluate this line integrals from alpha beta, so this is f prime gamma t, gamma prime t, and dt. Okay, so this is by definition. But what is that? This is just the derivative of the composite function. Okay? So this is the derivative of the composite function. Alright, and so what is that? So so this is the derivative, right? So we have f gamma beta minus f gamma alpha. Okay? But because it's closed, so gamma beta is equal to gamma alpha, so this is equal to 0. End of proof. Okay. Alright, so this is simple. Okay, so there is a remark. I have to say that for any A in C, and for all n in integer, n is not equal to -1, z minus a, n is the derivative. Is the derivative of z minus a, n plus 1 divided by n plus 1. When you take the derivative, you know the derivative equal to this one. If n is not equal to -1. Because if n is equal to -1, this is 0, right? It's undefined. Okay? So if n is not equal to -1, the derivative of this one is the derivative of this. Okay, so for any closed path gamma, right? Not only the positive oriented circle with center A, radius rho, right? It's very general that any closed path gamma. So for any closed path gamma, such that this A not in gamma star, so the image will not go through A. Okay? If n is less than or equal to -2. Okay? So because if n is minus, then Z cannot equal to A. Otherwise, it's undefined. So we just require. So if n is less than or equal to -2, then we require A is not in this cross path. But if n is greater than equal to 0, then it doesn't matter. But that's fine. No problem. Okay. Okay. Now by theorem 14.2.8, the integral z minus a and then dz, right? The integral. We find that this integral is equal to 0. Because that because this one is continuous, of course. So we prove. So this is what we have. So we extend our previous result to include gamma, which gamma can be any cross path. Because in the last section, we prove such an identity for gamma to be a positively oriented circle with center A, right? And radius rho up to rho. But here, we can extend the result to gamma, which is an arbitrary cross path. And it only requires that if n is less than -2, then A cannot be in the image. That's fine. This is the only restriction. Otherwise, this is true. Okay? And of course, n cannot be equal to -1. Of course, n cannot be equal to -1. Right. So this is the very basic beginning to the journey of Cauchy's integral theorems. And we will discuss the further theorems next week. Okay. So once again, I have to remind you that I will send you two supplements. One is for chapter 14, the other is chapter 15. And you have to read chapter 15, section 15.1 as early as possible. It's about Paul series expansion. Okay, so I see you next week. Oh, by the way, we will have a quiz examination next Tuesday.